Hi everyone, today we'll be learning about NDT, which is non-destructive testing. And there are a wide variety of methods that we use in NDT. Most applications include, for example, aerospace, detect cracks, which tells the condition of the aircraft, and also, for example, structures. We have a little structure here and we want to detect what is called a crack. Our yellow highlighted portion right here is a crack, and we can, for example, use different methods like for ECT, we so-called eddy current testing, RT, radiography testing, or even UT called ultrasonic testing. So there are different types of methods that we can detect this crack right here, which is not on the surface. So this is the surface of the material that we are testing, and this is what we call internal defect. So 5 types of NDT. This is what is most commonly used in the industry. And other than aerospace, there can also be welding checks. For example, we are welding a V-notch weld, and the welding has a little surface here, and you want to check for defects that are here, here, or even here. So it can be angle, it can be porosity, it can be a defect on the surface here. You can check for different types of defects based on the different types of methods that we use, which we'll get into this later. First off, we want to understand NDT. So imagine that you want to test an object for whether it has a damage, you suspect a damage. First off is surface breaking defects like liquid penetrant inspection and magnetic particle inspection or testing. Those last words can be interchangeable. So liquid penetrant is basically spraying liquid on the surface. First step, which is the penetrant. Second is to wipe it off. So you remove the penetrant and you apply another coating, which I will call it blue this time, and this one is the developer, to develop the cracks that the penetrant has penetrated into. So this is liquid penetrant testing or inspection, the ultrasonic, eddy current, and last but not the least, we have radiography, which is the most dangerous method because this one has the radioactive substances that we want to avoid, like iridium 192 and cobalt 60. So these are the radioactive substances. So these are called radioactive isotopes. But we'll get into all these later, so we don't have to worry so much. First, so let's take a look at more of the liquid penetrant thing. But first off, why are these so important? Why do we invest so much money into doing NDT? Why is the question that comes to your mind. Why do we do NDT? Well, NDT is first off to detect defects and damages. But this one can vary depending on the method. Second is to inspect components, which is critical because aerospace requires a high standards of safety, and we cannot allow a component to fail in the aerospace. So critical components can include like turbine, fan, compressor, etc., landing gear, even the fuselage section, because fuselage is what creates the high pressure. Because inside at cruising altitude you have, for example, almost like 0.8 bar, then outside maybe is around 0.4 bar, so the pressure will be pushing the material outwards, and this one may cause cracks to appear. Next is to also the monitor structural integrity, because we want to check for damages or degradation of the material. And then we have to comply, so this is regulatory compliances. So like it has to comply to Boeing, which is the original equipment manufacturer, to ensure continuous airworthiness. Airworthiness, seaworthiness, landworthiness refers to an ability for a plane to be able to safely transport passengers from A to B. It's worthy to be in the air. Car has to be landworthiness, a boat has to be seaworthiness, therefore an aircraft has to be airworthiness. So it also helps to reduce maintenance costs because NDT can detect early detection of defects or flaws. This is basically the why we do NDT. NDT is pretty important in any type of industry. For example, in the offshore industry where you are doing the welding, or the aerospace where you are dealing with titanium or even critical components on the aircraft. Now let's take a look at the MPD of the aircraft. Of course, in terms of maintenance planning document or MPD, it outlines the method of the aircraft, outlines maintenance protocol. For this one, you detect blah blah blah. In component A, you use what to detect, when to detect. So for example, the different types of schedules, the things to do. But for now, we want to check for NDT. Be many different types of NDT. As mentioned before, we have 5 types already. And you might ask, why don't you just use one type, like one size fits all thing? Though not really. So this is the question that comes in. Why use different NDT methods? So flaws refers to imperfections, like for example cracks and stuff. Let's take a look at, for example, subsurface flaws that exist underneath the surface of a material. So these are called subsurface. A welding face crack is surface breaking. Second is visual, with or without aid. So for example, magnetic particle testing uses UV penetrant versus under UV. Different types of visual inspection, such as under visible light. Some of the penetrant and developers requires UV light. Different types of methods, such as subsurface flaw, surface breaking, internal discontinuity. So like for example, discontinuity. So referring to the UA232 flight incident where the compressor blades actually cracked here is from alpha titanium inclusion. So alpha titanium inclusions right here would require a more specialized NDT testing. Our most best choice is radiography. Radiography testing will identify the inclusions. Alpha titanium inclusions will so-called irregularities in the structure, or you can even do very in-depth testing. And then also electrically conductive material, such as for example steel, aluminum. So you can use the eddy current testing method. So this will help you to test for your material here that we expose to a magnetic field that's passing through a coil like this. So this is supplied alternating current, which will generate a changing magnetic flux. So it's called d phi over dt. So it will interact with the conductive material and will detect whether the flaws can be inside. So for example, these are defects. The electromagnetic induction will change. Ultrasonic can detect, for example, homogeneity. Homogeneity means the uniform distribution of material composition. Geometric defects such as angle defects can be internal. So ultrasonic, we will use the angle beam for this. And then the choice of methods. Now let's go on to liquid penetrant testing. So, or what we call dye penetrant testing. This is actually very important, but this one is usually labeled under visual inspection. This is the defect right here that's shown, and the person can actually see this one because of, for example, a light source, and thus this is visible to the eye. That's why we call visual inspection. Liquid penetrant is simple because it can detect flaws in a short time. So like applying the penetrant, clean, developer to see. So why do we use penetrant? Penetrant will help to magnify the defect. So this is the original size of the defect. And when we use, for example, a dye penetrant, so we're just gonna go with a pink color or purple color, contrast the surface. So this is what we call the crack indication by penetrant developer. So it increases the size of the visual inspection, so it's easier to identify the cracks and flaws. So you can check for cracks, porosity, lapse, seams, pinholes, lack of fusion. These are all can be considered surface breaking, meaning that the defects can be visible with the eye, or not necessarily. You can see the defects without actually digging into the material. Penetrates out of the surface, so making it easier to see. What are the benefits, the pros and cons? High sensitivity to small surface discontinuity, rapid inspection of large parts. Liquid penetrant can be used for rapid inspection. Indications are produced directly on the surface. This right here is the crack that we can see on the surface. However, the cons is, as you can realize, only surface breaking. So if you want to detect a flaw that is underneath the surface, liquid penetrant wouldn't be able to do it. Non-porous, so like for example, a sponge, so no sponge like material. So some materials have sponge-like structures. These are not able to be tested by liquid penetrant because only then this surface right here, there is no pores. This surface is steel, and steel is a relatively non-porous material. Next is of course pre-cleaning is required, because let's say we have a welding defect here and we want to detect the crown. So this is called a crown. We want to detect some defect here. Defect detect. However, we are covered with a thin layer of rust, which I will represent with a kind of a brownish tone right here. So these are rust, because you would realize that steel rust, iron oxide layer. So to prevent this, we have to kind of scrape this surface out to make sure that our oxide layer is gone. So this may be a bit time consuming. For example, for some cases where your overhaul, you have a very rusted surface, very rusted bolt, very rusted material that you want to test using liquid penetrant. This is some considerations that you have to look for. And then also, because pre-cleaning is so important, hence the surface geometry or surface roughness have a huge impact. So a higher surface roughness may indicate as a flaw when your actual flaw is this guy right here. Because of the high surface roughness, this is exaggerated. You have a very high surface roughness, the liquid penetrant will interpret this as a flaw and this as a flaw. So it seems like you have two flaws here, but actually the only flaw that you need is this flaw. And this one is wrong. This is liquid penetrant inspection, very simple NDT testing method. So post-cleaning is required due to the chemical used in the liquid penetrant testing, which can be toxic also. Chemicals like, for example, aerosol sprays can be toxic on the type of material. Now they are trying to make sure that it's safe for the engineers to apply or something like this. Now let's move on to second, magnetic particle inspection. Magnetic particle inspection is slightly more complicated this time because instead of just using a penetrant and a developer, we have extra things to do. But first off, we want to look at a materials hysteresis loop. What is hysteresis in general? Hysteresis refers to a condition where a material response to magnetic field depends both current past conditions. To summarize this, it refers to factors affecting the magnetization of the material, and it's a very interesting curve that looks like quadratic equation but also a cubic equation. So we'll draw a graph, a Cartesian graph, and the vertical axis is B field, which is the magnetic field, B is the flux density, and H is the magnetization force. We will draw points on the curve, on the graph. 1, 2, 3, 4, 5, 6. And what we do is to join this curve like a continuous loop. First step, ferromagnetic material starts at the origin. This is your starting point. We shall use a blue marker to highlight. So this is A, starting point. Then when you magnetize the material, it will go to B. B is what we call the saturation point. Regardless of how much force you magnetize it with, the B field will remain the same. A very little increase in B field. Even after you continue increasing the H increase and increase, it will still remain the same. Point B is where you disconnect the H, and this is called the retentivity at 0 H. It refers to how much magnetic force when you stroke a magnet, when you stroke a piece of iron with a magnet. So this is a north, south, and when you stroke it like this point right here will be north and this one will be south. So the south will gather on the left hand side and the north will gather on the right hand side, because this is where the last point of contact is to the iron rod, which is south here. So the south would not gather here, it will want to migrate to the left hand side of the iron block. And once you remove the magnet after temporarily stroking the magnet, it will become a magnet even if you take out the magnet. So this is called retentivity, in which its inner ferromagnetic, which consists of small magnets, are aligned like this in reference to direction south and north. So this is called saturation, in which the magnetic fields are already aligned. Further magnetization just makes the magnetic field strength the same. Point C, coercivity. Coercivity refers to a point where the B field is 0 when there is negative magnetic field, meaning flip the direction of the magnet. So now you flip it north and south. So right here what it will do is that the north would now want to be here. The south is already here. When the north reaches here, it would want to repel the north here. This is called a repulsion force. So if you take a look at this, the magnetic field will become more disorientated. So one is like this, one is like this,
one is like angled north-south here, angled north-south here.
So this is called the coercivity. It's where the magnetic field strength cancels out. So you don't have a pole. It's just a metal without magnetic poles. So point D is saturation in opposite direction. So instead of making it coercive, now you want to stroke the magnet again. So you continue to stroke the magnet in the same direction, north-south here. So this will make sure that the ferromagnetic particles inside the iron align in new direction, because since your magnet has north here, south would eventually want to be here because unlike poles attract. So the last point of contact with the magnet to the metal is where the poles will be at, opposite poles. So this is point E, which is retentivity in the opposite direction. So after you stroke multiple times, it will retain the magnetic field, and hence the iron pole becomes magnetized, where you have north-south at one corner, even after taking the magnet off. So this is called retentivity. So let's draw it out in stages. To draw in stages, we'll be writing out a number for each of them. So I'm gonna use a blue pen, light blue pen, or better contrast next time, a purple pen. Stage A, B, and then C, where we stroke the magnet in the opposite direction. Then D, it becomes a saturation in the negative direction, and this is the retentivity in the negative direction. Then the whole cycle repeats again. Flip the magnet, stroke it again. If the hysteresis loop is wider, so the area between this is wider, you have different factors that affect magnetic particle testing. A wider hysteresis loop, so this means that your retentivity is higher, so its ability to penetrate through the material is lower. Think of it as we draw a very narrow S-curve, very narrow. So this is our hysteresis loop, super duper narrow, versus a thick hysteresis loop. This one has higher saturation, low permeability because of the material's inability to have more magnetic flux. Thus, we have higher residual magnetism because the hysteresis loop prevents the magnetism from dropping back to zero unless we have to use a very powerful demagnetizer to demagnetize. Narrow hysteresis loop is basically the opposite of all these. High permeability, low retentivity, low corrosivity, low reluctance, and low residual magnetism. If we want to detect flaws in an object, we will have to magnetize the object in different direction. For example, we apply current here. By our right hand rule, the magnetic field would go around in loops facing upwards, and we have a defect here. And yes, because since the magnetic field cuts the defects, it is able to test longitudinally. So this is your B field and your current. This will be able to test surface defects. However, if we have a defect that is, for example, angled like this or like this, then this way of magnetizing wouldn't work because it's unable to detect, because it doesn't cut through the magnetic field. Instead, it's parallel to the magnetic field. Instead, we'll have to apply the current in a coil like format. So we draw a solid line for the coil, and we apply a current like this. So this way the magnetic field, our magnetic field direction would be here. So this way the defects that are oriented perpendicular to the magnetic field will be able to be detected. So this is the B field here. This way it cuts through the material. So most importantly is whether our B field can cut through the defect. Then you have to demagnetize after you test defect. Similar to how we demagnetize the material, how we clean the defects from the liquid penetrant, we also have to clean from the magnetic material. To demagnetize, for example, you can use heat, alternating current, even a vibrational demagnetization. Mechanical plus magnetic field. Demagnetize, for example, heat above Curie temperature, in which it loses magnetic property. Or alternating current, demagnetization, degauss. Advantages of MPT includes almost the same as liquid penetrant, but there are actually noticeable differences. The pro and con. Of course, every NDT method has pro and con. So first off, it's complex shape. Remember how we draw a cylinder here? This is a cylinder and it has defects here on the surface of the cylinder. Yes, you can actually check for the defects here. Subsurface, surface breaking. So it doesn't have to be surface breaking. Even a subsurface damage in the magnetic field right here, it can make the magnetic penetrant magnetic die react to it. Of course, this will be interacted with, for example, the magnetic die. So the die would react to the defects. So these defects right here would create a, for example, a flaw indication. The angle also affects this. So make sure that the angle is lesser than 45 degrees for the circular rotating magnetic field. It's more than 45 though. This is more than 45. We have to use a straight line magnetic field to be able to cut through the material. Only when the B field cut through the material, it can interact with the material easier. If it's just parallel to the field, it doesn't do much. We are not using dye penetrant where we actually inspect the surface. We are using magnetic to actually detect surface breaking defects. They are close to the surface but not necessarily on the surface itself. So this way, if for example you have rust here, it doesn't interact with the magnetic field at all. It just cuts through the thing. So this way, when your magnetic field runs through the coil, it will interact with defects. Sometimes cleaning the surface of the workpiece or the material to be tested is a bit troublesome. Next is of course cracks. Pits and porosity can be located within coatings. A rust is like a coating. So for example, if you have rust on the surface of the material, you can still use magnetic particle testing, whereas the liquid penetrant might not give you favorable outcomes. But however, notice that we use magnetic. So this one, we have to use ferromagnetic materials. Ferromagnetic materials doesn't mean it contains Fe. It can be iron, of course, nickel, and cobalt. Nickel and cobalt doesn't contain Fe, so obviously ferromagnetic doesn't equal to Fe. High current for magnetizing large parts. And most importantly, you don't know where is the defect located in. Direction of magnetizing is important. Do you magnetize the object by applying a current so that the B field can be generated like this, or do you magnetize it by coiling around a material so that the magnetic field can go around like this? Of course, this is very important factor. So of course, components must be demagnetized after inspection, which can also be a bit troublesome because you again have to use these methods right here to demagnetize the material. That's pretty much all for the magnetic particle testing and liquid penetrant, and we will continue on with ultrasonic, eddy current, and radiography because this part is the most important one. Let's see you in the next one.